All right, example 2, we're going to do a half-life problem. And any time you're talking about half-life, carbon dating, any of these things where we're using the decay rates of different elements, we are assuming that these rates of decay are constant. That is an assumption, a little difficult to verify that these things hold fast for thousands of years since we've not been studying them that long. But it seems to be a good assumption, at least for modeling short-term type things. And so we're going to look at an element, radium-226, and we're told that the half-life of radium-226 is 1,590 years. And what does that mean? It means that you start with a collection of radium-226 by weight, not by like area, but I'm going to visualize the area here. You start with a collection of radium-226 and you wait almost 1,600 years and you'll have exactly half of what you started with after that time has passed. So it's decaying, and we're assuming that the rate of decay is proportional to the amount present. Not stated in the problem, but that is the underlying assumption. So we're starting with 100 milligrams of this radium-226. And it says find a formula for the mass that remains after T years. And so I want you to realize in part A, we know right away that m of t, our formula, is going to be m naught e to the k t. And we're actually told what m naught is. That's just m of 0. That's the initial starting amount. So this constant is always the sort of starting population, or in this case, the starting amount of whatever element we're working with. So this is exactly 100 e to the kt. So all we need to do to work out A is to find k. Let's actually say that we need to find k. All right. So what do we know? Well, we know that m of 1,500, whoa, let's scroll this forward. There we go. We know that m of 1,500, when 1,590 years have passed, we're going to have half of what we started with. We started with 100, so we're going to have exactly 50. But m of 1590 is what? M naught, which was 100, sorry, 100 e to the k times 1590. That's what m of 1590 is. This equals 50. And so I'll go this way. That means that E, I'm going to write it 1590k equals 1/2. Now I want to solve this equation for k. You can do that. I'm going to take the natural log of both sides. And so I get 1590k is the natural log of 1/2. By the way, the natural log of 1/2 is ln of 1 minus ln of 2. But ln of 1, for the record, is 0. So this is negative ln of 2. You expect k to be negative. And the reason is that this radium-226 is decaying. It's getting less and less. And if you left natural log of 1/2, you could, but you might not realize that's actually a negative number. Anytime you look at the natural log of something less than 1, it's going to be negative. So I reduced it to this, and now I can easily solve for k. K is going to be minus ln of 2 over 1590. I almost said k. That's not what we want. 1590. There we go. So that's my k. And so now I'm finally ready to answer part A. I can say the formula for the amount of radium-226 after t years have passed is 100 e to the minus ln of 2 over 1590 times t. Okay. Part B. Let's scroll back up and read it together. Hopefully we're able to print a copy of this out. So it says, find the mass after 1,000 years, correct to the nearest milligram. And so you're quite literally just plugging in m of 1,000, and you're going to get 100 e to the minus ln of 2 times 1,000 over 1590. You can use a calculator, and I got 65 milligrams. I said equals. That's not true. It's roughly equals, wiggly equals 65 milligrams. So it said to the nearest milligram, so I just rounded mine to 65. So quite literally, the B, you're just plugging in 1,000 into your formula, and then you just estimate it on a calculator. I'll let you do that. I like part C. It says, when will the mass be reduced to 30 milligrams? So, well, when is a question of time. So you know just the question when. It says when. That means your answer should be at t equals. And so m of t tells you the amount present at time t, and you want the amount present at time t to be 30. And now we're going to solve this equation for t. And by the way, right, m of t we know is 100 e to the minus ln of 2 over 1590t equals 30. So I get e, I should write a little bit bigger here. I get e to the negative ln of 2 over 1590t equals what? 3 over 10, 0.3 if you will. And so let's see, I take the natural log of both sides. On this side I get minus ln of 2 times t over 1590 equals ln of 3/10 or just 0.3 whatever. And so you can solve, let's kind of draw a line here like this. I'm going to go up here now, and I get what t equals. When I solve for t, I get 1590 ln of 0.3 over, that's negative actually. We'll put a negative upstairs, and then over ln of 2. And you can use your calculator, and you can get t is roughly 2,762 years. So we've got a long wait to watch our little bit of radium-226 decay down to 30 milligrams. But after 2,700, a little over 2,700 years have passed, and that's when there'll be 30 milligrams left. All right, so that is the end of example 2. Great job. One last example, and then we're finished with the section, and you should be ready to tackle the homework.